Welcome viewers, welcome back to O3 School JAMB tutorial classes. Remember, this is an online class brought to you by O3 School. Now, in today's part of physics, we'll be talking about mechanical properties of solid. Now, under mechanical properties of solid, we'll be talking about elasticity. Now, what do we mean by elasticity? Now, the elasticity is the property of a material that enables that material to return to its original shape or size after being stretched or after undergoing deformations. So when a material undergoes deformation and that material is able to regain its shape or size after being stretched, so that material is said to exhibit what? Elasticity. Now, what do we observe? We observe that, for example, if we say elastic material and plastic material. Now, for elastic material, they return back to their original shape after being stretched. Now, when there is an applied force on such material, what happens is that the material elongates. The material do what? Elongate. So the material elongates. Now, when it elongates, just like a rubber band, a rubber band, or the one we locally call maybe rubber ring or so. Now, what happens is that material has the tendency to be stretched. Now, when the applied force is being, the deforming force is removed, what happens is that the rubber band returns to its original shape. Now, but for plastic materials, when they undergo stretching, they do not return to their what? Original shape. So that means the plastic materials undergoes permanent deformation. For permanent deformations, that means the material do not return to its original shape, did not return back. The size and shape, you can't get the shape and the size either. Now, but for elastic material, when elastic material undergoes deformation, the deformation is just temporal. It's temporal. So the material will come back to its what? Original shape. Okay. Now, elasticity is a property of a material that enables it to return to its original shape, as I've earlier said, after the deforming force is removed. After the deforming force is removed, the material returns back to its original shape. Now, someone may ask you, why are we studying the mechanical properties of solid based on elasticity? Why? The reason is that mechanical materials, they are being used in constructions of buildings and bridges. Now, not just that, if we talk about the elasticity of a materials, right? Bridges constructions involve concrete and steel, iron rod and steel, concrete. Now, this material, they are subjected to load. What do you mean by load? You have a bridge. What happens is that trucks and the cars, they move along this bridge. What happens is that this material, they are being subjected to force. Now, when they are subjected to force, how do they behave? How will this material behave when they are subjected to this force? So that is why we are studying the mechanical properties of solid. So for bridges, we need to study the behavior of this material using the constructions and design so that we'll know the durability and how they are able to withstand pressures or forces from applied load. All right. So now, as I've earlier said, elastic material, they are material that regain their what? Their shape and size after being stretched. while plastic material, they undergo deformation permanently. Okay, plastic material undergo deformation permanently. They do not regain their size or what, or shape after being stretched. All right. So temporary deformation in shape or sizes, body returns to its original form. That is elastic deformation. So that means elastic material undergoes elastic deformation, while plastic material undergo permanent deformation. All right. Now we have elastic limit. When you talk about elastic limit, the maximum stress a material can withstand and still return to its original shape. But what happens when the elastic limit is exceeded? The material cannot return to its what? Original shape. Such material may undergo plastic, or such material may undergo fracture. Either there is a fracture or rupture. Okay. Let's see. There's a law that governs these mechanical properties of solid materials, and that law is Hooke's. We have Hooke's law of elasticity. Hooke's made some discoveries on the mechanical properties of solid. Hooke's told us that the force that is applied to a string is directly proportional to the extension. So the force you apply to a string is directly proportional to the what? Extension. Provided the what? The elastic limit is not exceeded. When the elastic limit is exceeded, the material may be subjected to rupture or fracture. So in machine designs, like the shock absorber, they are designed in such a way that they undergo temporary what? Deformation. So immediately you are passing through maybe a deplorable road, or where you have multiple potholes. What happens is that there is a shock absorber between the wheel of a tire that try to what? That try to absorb the shock. Now, when the shock is absorbed, what happens is that the spring undergoes Hooke's law. Now, when the spring undergoes Hooke's law, there is a tendency that an extension is produced. So what Hooke is trying to tell us is that we need a material that can withstand stress. So when a material, it's just like when you're talking about strength of materials now. You have maybe a 3-story building. When you get to the 2nd-story building, before the 3rd-story building, you are trying to add load. You are adding load to the 2nd-story building. Now that 2nd-story building, why is it able to behave when other loads are being subjected on it? Is it that the body will collapse? Does it undergo fracture? The material you are using, how durable they are? Are they stiff? Are they flexible? Are they durable? So all these mechanical properties are put into consideration during constructions or designs of what? Of machine. Because as time goes on, those machines will be subjected to what? To force or pressure. Now, what Hooke's law says is that he said the force is directly proportional to the what? To the extension. There is a linear relationship that the force is directly proportional to the what? Extension. So this is a direct variation. Direct variation. Okay? Now for direct variation, we know we'll have a constant. F equals to K E. So if F equals to K E over E, by the time this cancelled, K is equals to F over E. So this is force applied. This is applied force and the elongation. Apply force and elongation. So we have elongation elongation. Now this elongation is same thing as what? Extension. Extension. Okay. Now, if K equals to applied force over extension, that means that what happened if, now from this relationship, if the force increases, the extension produced also increases. So that means increase in force will lead to increase in what? Elongation. Maybe for example, I have let's make an instance. Okay, let's say if we have more and more states, for example, let's say K becomes F1, E1, F2, E2, F3, E3. For example, maybe I have an applied force of 10 Newton, giving me 1 centimeters. If I have another force of 20 Newton, giving me 2 centimeters, another force of 30 Newton, giving me 3 centimeters. So that means the more the increase in applied force, the more the what? The more the elongation. And the lesser the force, the lesser the what? The lesser the elongation. So they are directly what? Proportional. Okay? So let's see some diagram representation, some experimental representation. So let's assume we have a rigid body. It's a rigid body. Then we have a spring. I said this is a spring. And this spring houses 100 Newton. So what happens if I have another spring? And this one is, let's say, 40 Newton. $60 Newton. I have your spring. So this here to here, we have length. Here also. So this is a rigid body. This is a rigid body. Then we have spring. We have springs. Then this load. We have another load. We have another load. Now, what happened is that, let's assume this is F1, F2, and F3. Now, let's say for F1, we have a load of 100 Newton. Now, because this load has more weight, rather, the load has more weight, what happened? There is much elongation coming down. Now, here we have a decreased load of 40 Newton. What happened? The extension reduced to this point. Now we have another load of 60 Newton. The extension from the spring gets to this point. So what do you observe is that the more the force, the more the extension. The lesser the force, the lesser the what? The extension. So what happened is that here is our length, the equilibrium length. So the more masses, if this mass is up to 200 Newton, this spring will go down. Okay? So that means that there is always L plus what? Plus E. So if the actual length, let's assume the actual length is 4 meters, then there's an extension of maybe 0.01 meters. So we have 4.01 meters. Now, because of the force has extended the length that was 4 meter by 0.01 meter. So the 0.01 meter is the elongation. Okay? The 0.01 meter is the what? Is the extension that is produced as a result of what? The applied force on that material. Okay? So we can definitely say that that F equals to what? KE. Okay? Where K equals to what? F over E. Our K is the force constant. The force what? The force constant. So Hooke's law helps us to predict how structure bear their weight and responds to various forces. Hooke's law helps us to do what? Help us to predict how structures bear their weight, bear their body. Body, you are talking about the entire load on a particular structure. So Hooke's law has experimental what? Advantage or importance in mechanics, engineering, designs of what? Machines and structures, bridges. Okay? Those are the advantages, applications of what? Elasticity. So, application of elasticity, bridges and building. Now, buildings and bridges, there is need for steel. There's need for steel. Why are we using steel? Why is it steel? Because it has less Young modulus. It has less what? Young modulus. We'll see about that when we get to Young modulus. Spring and shock absorber. Now, measuring instruments. The application of elasticity helps us in measuring an instrument. They enable instrument to measure accurately. Okay? Now, another thing is, when a force acts on a material, it causes stress. This stress produces strain and change in length. Okay, we also talked about some terms relating to what? To elasticity. But for this aspect of the topic, just know that increase in applied force will also lead to increase in what? Elongation. So let's see an instance. Let's say instance, if F1 is 30 Newton and F2 is 60 Newton. Okay, let's say extension 1 is 1 Newton, 1 meters. If extension 1 is 1 meter, what will be extension 2? Okay, so what we do, we know that F equals to KE, right? So K is F over E. Applied force over extension produced. So if K equals to F over E, we have F1, E1, F2, E2. So K is a constant. So we now have F1 over E1, F2 over E2. So we work with this. At different interval. Now, when a force of 30 Newton was applied maybe to a string, there was an extension of 1 meter. Now, what happened when a force of 60 Newton is applied? We should be expecting 2 meters. But let's see from our solving. F1 is 30, E1 is 1. Now, when F2 is 16, we don't know E2. Okay, so 0 cancels 0, 3 here 1, 6 here 2, definitely is 2. So E is what? Is 2. So that means that it's a direct proportional analysis. It means that when the force F1 is 30 Newton, we have an extension of 1 meter. When the force now increase, so we should also expect the elongation to also increase to 2 what? To 2 meters. 2 meters. So that's why Hooke's law says the force that is applied to a string is directly proportional to the extension that is produced, provided the proportionality limit is not exceeded. If it's exceeded, the material might undergo plastic region. Or if there is maximal load say applied, the material may undergo rupture or what? Or fracture. Okay. So now we have terms employed in elasticity. We have terms employed in what? Elasticity. So the first one, you talk about stress, strain, and Young modulus. And this is gamma. Then stress is sigma. Stress is represented in sigma, while strain is what? Epsilon. Strain is what? Epsilon. Now, when there is stress, one thing you need to understand is that when there is stress in a material, it will lead to strain. If you are stressing a material, it will lead to what? To strain. Because strain is epsilon, and it's dl over L. Change in length over original what? Over original length. Now, this change in L is the extension, is the elongation. So we can say extension over what? Over length. Okay? So when you stress a material, the material will undergo strain. And in design, we don't want strain. So we need to study how material undergoes stress. How? For example, you have your bridges, as I've earlier said, under the applications of elasticity. You have a bridge, you have a house. What happens when the building undergoes stress? What happens when the bridges also undergo stress? What happens when the rail track undergoes what? Stress. When they undergo stress, as a result of applied force, it will lead to strain. And when there is strain, there will be what? Elongation. And when there is elongation, that material, is it able to return to its original shape? We need to study for the fact, we need a material that will be able to return to its original shape after undergoing what? Stress. That is where steel comes. The steel material comes. The steel material, they are able to undergo stress until return back to their original shape because they have very small Young modulus. We'll come to that later. Now, what is stress? Now, this strain, we can have, strain is extension over length. Extension over length. Right? Then stress, you are talking about pressure. Stress, you are talking about pressure. And that implies that you have what? Force over area. Force over what? Over area. So when a material undergoes stress, you are talking about force over area. Area, a particular, an exact surface. It could be a square surface. We have maybe something in this form. Oh, my marker. We have something in this form. I'm applying what? Force. If I apply force to this area, let's say this is 1 meter and this is 1 meter. Normally, my pressure is force over area. So let's assume this force is 1 Newton. Definitely area, if this is a square, area is also 1 meter square. So definitely my pressure is 1 over 1. So I have 1 Pascal. Pressure is what? 1 Newton per meter square. So when this material undergoes stress, right? If it's undergoing stress, if there's more stress, the area will reduce. More pressure, area will reduce. So a particular surface that has been designed, when there are more pressure, more stress, the area will be reducing. So there will be maybe a slight cut. There will be a slight cut here. There will be a slight cut. So if there's a slight cut, it's as a result of the fact that you have stress. So when there is stress, this material now will undergo what? Strain. Because it's undergoing strain, what happens? There will be extension over what? Over length. So now how do we get Young modulus? Now Young modulus is now tensile stress. When you say tensile stress, maybe the body is being stretched. Okay? The stress and the strain can be compressible. Compress, coming together, is being compressed. Stretch is being elongated. So we can have a tensile stress and a tensile strain. So Young modulus of elasticity, we are coming to Young modulus now. Okay. So Young modulus of elasticity is equals to tensile stress over strain. So that means our Young modulus is what is stress? Force over area divided by strain divided by E over what? Over L. Okay. So that implies that we now have Young modulus is F over A times what? L over E. So FL over AE. So this is Young modulus. So the Young modulus is used to know what's the essence of this Young modulus. It's used to measure how stiff a material is. Oh, we want to use this steel. Is it stiff? We want to use a rubber. If you can't use rubber for bridge constructions because they undergo elasticity very easily. With a little force, they are already stretched. So that's why we may likely use material like steel in constructions of bridges and maybe buildings of different kinds. So the Young modulus is used to measure how stiff a material is, or is used to know the elasticity of that material. How much a material can resist stretch. How much a material can resist stress. By this stress, that's how much a material can resist an applied force. Or is it that the material will compress when a force is being what? Is being applied. So that's the essence of the Young modulus. So it is very important to know the Young modulus of a material so that when the body is being subjected to force, we will know the causes of that stress, and because it's definitely the stress will lead to what? Will lead to strain. It's because of stress we have what? We have strain. Okay, so we also have elastic potential. Elastic potential. Now, elastic potential, you're talking about energy stored in an elastic string. So, elastic potential. Elastic potential is UE. Okay? Is UE. And UE is 1 over 2 FE. 1 over 2 FE. This is energy stored in a what? In an elastic material. So we know from Hooke's law, we know that F equals to KE. We know that F equals to KE. So definitely, if we take this to be equation 1 and this to be equation 2, definitely we can say UE equals to 1 over 2. F is KE. So KE dot E. So we have 1 over 2 KE squared. Now, remember that elastic potential can be converted to kinetic energy. Elastic potential can be connected to what? Kinetic energy. Elastic potential can be connected to kinetic energy. For example, a catapult. If I need to, maybe I have a catapult, just do a sketch like this. If this is a catapult, for example, then I have maybe a stone. So what happens is that the catapult undergo elastic potential before the stone is released. Immediately the stone is released, the stone gains kinetic energy. Remember, kinetic energy is the energy of a body in motion. The energy of a body in motion is the kinetic energy. So that means elastic potential, so 1 over 2 KE squared is now converted to what? 1 over 2 mv squared. So this is elastic potential. You see some of the JAMB questions we are going to be solving and WAEC question involve elastic potential to kinetic potential. Okay. Then we also have stress and strain curve. Okay. We have stress and strain curve. Under elasticity, we are studying on elasticity. So we have stress and strain curve. So we have something like this. Let's say point of origin, our sigma and epsilon. So sigma here is force over area. Then epsilon is the L over L. So at this point, that means here is stress. We have stress. While here, we have strain. As strain occurs as a result of what? As a result of stress. Now, for example, you have a wooden bridge. Wooden bridge is mostly common maybe in the rural area. Now, this wooden bridge, as time goes on, it undergoes what? Stress. Okay? It undergoes stress. And because of the stress, the material may undergo tension. The material may undergo tension or what? Compress. It may undergo tension or compression. Now, as a result of that compression or stress, as a result of stress, the wooden material undergoes strain. There will be change in length over what? Original length. So as time goes on, the material deforms. The material deforms as a result of much what? Stress. Now, if that material were to be steel, for example, because steel has less Young modulus, so is able to retain its shape and size after being stretched. Now, the wooden material is unable to regain its shape or size after being stressed. The material undergo collapse or deformation. So now let's see. At the beginning of this graph, is linear. Then we have a sharp bend, goes this way to the plastic region, then to the rupture region. So at this point, let's say here is A, and this point is B, this point here is C, let's say here is D, and here is E. Now, from this point, I can shade like this. This point is called the plastic region. Now, for plastic region, I've told you several times that the plastic regions undergo permanent deformations. There's no way you stretch plastic is not elastic. Elastic is temporal. Elastic can undergo temporal deformation and come back to its original shape or size. But from the region of B to E, it is called plastic location. So BE is called plastic location. Either I call it plastic location or plastic domain. Now, from the region of O to A, what do we observe? Is proportional. Is what? The stress is proportional to the what? To the strain at that point. So there's a linear what? There's a linear relationship. So we can say OB, OB is equals to what? Elastic region. OB is elastic region. Okay? Now, you have a material that is being undergoing stress. That stress is directly proportional to the strain. That's why you have a linear relationship from O to what? To B. I mean, from O to A. Now, from O to B, it is called elastic region. That means after being stretched, the material is able to come back to its original size or shape. But from B to E, from D, you even have a maximum load. You have the maximum load. That means the material has undergone much stress. Now, from B to E, what you have is the plastic location. Now, when the material is still subjected to more stress, we call it maximum load. At that point, at point E, the material may break. We have the breaking point. The material may even break. And when it breaks, it is called the rupture. The material what? Rupture. Call it the rupture. The material rupture, or we'll call it the breaking point. So from O to A, there is a limit. That's a limit of proportionality. Then from B, that is the elastic limit. But what happens if the elastic limit is exceeded? The body may definitely break down. So elasticity is a property of a material whereby the material is able to regain its size or shape after being stretched. After being stretched, or after the force, the applied force is removed, that material is able to regain its size or what? Or shape. But if the material is unable to regain its size or shape, it becomes a plastic material. It becomes a what? A plastic material. So in engineering or in science, there is need for us to study the strength of material before being used. You need to know, okay, if I'm using a particular material, I'm using rubber for bridge constructions, and I have trucks that have thousands of tons carrying thousands of loads passing through that bridge. Will that bridge be durable? Does it have durability? Is it durable? Will it last long? Will the rubber be able to be subjected to stress? So all these are put into what? Consideration. If you check the shock absorber is not made up of rubber. If it's made up of rubber, it will not even last long because rubber has very high Young modulus. After much stress, it will undergo elasticity easily. And when it undergoes elasticity easily, it is subjected to what? To rupture if the elastic limit is exceeded. That is why we have the steel industry. We have the steel industry, which are much conversant in the whose material they are mostly conversant in the constructions of bridges and structures. Okay, so we have a stress and strain relationship. Okay, so this is called the stress and strain curve. All right, so let's see problems from our JAMB app. Please do well to download the app from Play Store, as I earlier said in my previous video, and equally activate. You see multiple choice questions on both WAEC and JAMB from Elasticity. So let's solve problems. Okay, we have let's see. Okay, we have a problem from, I think this is JAMB WAEC 9. Okay, we have a problem from, this is WAEC. We are still solving problems from elasticity. So we have WAEC 2025 9A. It says state one difference between deformations and elasticity. A deformation is just the change of shape. Okay, there's an effect of force that causes a change of shape. We don't know whether the material undergoes, we don't know whether the material regains its shape or size. But for elasticity, the material undergoes deformation and just maybe a temporary deformation and still retain its size and what? And shape. Okay? So that is maybe based on definition. Based on definition, the elasticity is the property of a material to regain or to return to its shape or size after what? After the deforming force is being removed. Okay? Now, in terms of maybe their nature, deformation is an effect. It describes what happens to material when force is applied. Then elasticity is a property that tries to test us about the behavior of that material. The behavior of that material, that's what elasticity tells us. I'm applying a force. That is an effect. I'm trying to deform that material. But now, what is the behavior of that material? Is it that the material will regain its size after that force is applied? Or, sorry, after the force has been removed, will the material regain its size or shape? So that's the difference between deformations and elasticity. Now, again, under reversibility, deformation may be reversible or plastic. Deformation can be reversible or plastic. But for elasticity is always reversible. Elasticity is reversible. It's the tendency that of a body regaining its size or shape after the what? The stretch force is removed. So for deformation, is two things. Deformation is that it can be permanent, it can be temporal. Okay, it can be both permanent and temporal. If it's temporal, that means it's exhibiting the characteristic of what? Elasticity. But if it's permanent, that means it takes the features of what? Plastic materials. So that is that from that. Then we have another question again from 2000 WAEC again. WAEC 2001, question 11B, BI. It says state Hooke's law of elasticity. Now, Hooke's law of elasticity states that we can state it mathematically. I can just say, okay, mathematically, F equals to KE, right? Or I can say F is directly to E and F equals to KE, where K equals to F over E. If I have two or more states, I have F1, E1, F2, E2. As I've earlier said, now the Hooke's law tells us that the force that is applied to a string is directly proportional to the extension that is produced, provided the elastic limit is not exceeded. If the elastic limit is exceeded, the material may move to the plastic region. Moving to the plastic region means it's no longer coming back to its original shape or size. And after the plastic region, if the material is still subjected to maximum load, the material may undergo rupture or breaking point. So for more explanation, F equals to applied force, then E equals to elongation or extension, and K is force constant. Where K is what? Force constant. So that's that on WAEC 2001. So let's see more questions. Now we have another question. This one is, I think, is multiple choice. 2015, question 2. It said material can be stretched and still return to their original forms when the stress force are removed, are said to be dash, elastic, elastomer, plastic, thermoplastic. So the correct answer there is what? Elastic. Elastic material can be stretched and still return to their original forms when the stress are removed. Is that okay? So the correct answer is what? Elastic. So 15, the correct answer there is A. And A is what? Elastic. Okay. We have another question from WAEC 2019. WAEC 2019, question 1. Question 1. It said a stone of mass 20 gram is released from a catapult. So this is elastic energy or elastic potential to what? Elastic potential to kinetic energy. How do I know? Because of the word catapult. Catapult undergoes elongation. Undergoing elongation as a result of elastic potential. Then when the stone is released, there is a kinetic energy. And when there is kinetic energy, we have 1/2 mv squared. You must know the relationship. Now, as the stone moves with v velocity, the stone has a mass. So 1/2 mv squared. Now, so from the parameter we're given, the mass is 20 grams. Mass is 20 grams. It's released from a catapult whose rubber is stretched through 5 centimeters. So we have extension. The extension is 5 centimeters. So that will give us 5 over 100, 0.05 centimeter. Which other information? Now, if the force constant of the rubber, that means K, force constant, K, is 200 Newton meter inverse. Because we know that F equals to KE. So K, force constant, is F over E. So we have Newton per meter. So that's what we have there. Now they say calculate the speed which the stone leaves the catapult. When the body is in motion, the body is moving with the help of kinetic energy. So that means we need to calculate the kinetic, the velocity at which the stone moves from the catapult. So we know we have a relationship that if elastic potential equals to kinetic energy. Now, what is elastic potential? 1 over 2 Fe. 1 over 2 mv square. We know that F is equals to Ke. So we have 1 over 2 Ke square. Here we see F, we put Ke. So we have 1 over 2 mv square. So half can cancel half. So definitely we have mv square equals to Ke square. K over m. Let me write this way. So this is V. mv square over m over m. This can go. So which implies that what? Our V square is equals to Ke square over what? Over the mass. Now we have, okay, let me clean here. Okay. So we have V square equals to Ke square over m. What was the force constant? So K is 200. The extension is 0.05 square. Then the mass is 20 grams. So that means 20 times 10 raised per minus 3. Why am I multiplying with 10 raised per minus 3? So that we can have the mass in kilograms. So definitely what do we have? We have 200 times, let's take our calc. So 0.05 times 0.05 times 200. So we have 0.5. So everything at that top is 0.5. 0.5 over 20 times 10 raised by 3. So let's say times 1,000. We have 500 over 20. 0 cancel 0. So we have 25. So if we have 25, so V square is 25. So the velocity is plus or minus what? 5 meter per second. So if we take the square root, so our velocity is 5 meter per second. Okay. So the correct answer there is 5 meter per second. That's the velocity. All right. So let's see another question. This is another one from WAEC. Okay. A rubber gun. This is 2025. WAEC 2025. Part 2. Question 9C. A rubber gun is used to project a stone of mass 40 grams. So the mass is 40 grams. Now, if the rubber of the gun has an elastic constant, so elastic constant K is 350 Newton per meter, and was stretched 4 centimeters. So there was an extension, 4 centimeters. Calculate the stone speed of projection, just like the one we saw just now, okay? So this 4, we can divide by 100, 0.4 meters. Then this 40 over 1,000, this cancel this, 0.04 kilograms. So since the rubber is a rubber gun, the rubber may have some kind of elastic potential. So we can say UE is equals to KE. UE, elastic potential. So 1 over 2 FE equals to 1 over 2 MV squared. Okay, so 1 over 2 F, we can have 1 over 2 KE squared, 1 over 2 MV squared. We need the velocity at which the stone is released from the rubber gun. So this can cancel this. So let's come over here. KE squared. The first constant is 350. Okay, 350 times the extension produced, 0.4 square, then equals to the mass. The mass is 0.04 times V square. Okay, times V square. So what do we have? We have, let's use our calc, 350 times 0.4 times 0.4. We have 56. So 56 over 0.04 equals to V squared. So divide 56 divided by 0.04. We have V squared is 1,400. So V is square root of 1,400. Okay. So the 1400. So V is about 37.4 meters per second. So this is the velocity. This is the velocity at which, so let's see, 350 times 0.4 square. Okay. The mass is 40 grams. 0 cancels 0. 4 over 100, 0.04. So this is the velocity at which the stone is being released. 37.4. All right. Did we convert? Sorry. This is supposed to be 0.04. Likewise, so there's an error. 0.04. So here again, 0.04. Sorry. So what are we going to have? 350 times 0.04 times 0.04. So it's 0.56. 0.56. So here should be 14. 14. So that should be around 3 points. So let's see again. 0.56 divided by 0.04 is 14. So it should be 3.7. 3.74. So that is the velocity at which the rubber band is converted to the kinetic energy of the stone. The velocity at which the stone moves is about 3.74 meter per second. Okay, let's move ahead. Let's see other questions. Okay, let's see from JAMB. We've done some from WAEC. Let's see some questions from JAMB. Still on the O3 School app. That's where I'm picking some most of these questions. If you want more of the questions, you can do where to install the app from your Play Store, and likewise do where to activate the app. So let's see more questions on elasticity from JAMB. JAMB elasticity. Elasticity. Remember, elasticity is a property of a fluid. Property of a material to regain its shape or size after which the material has been what? Stretched, or after which the deforming force has been removed. So the material regain back its shape or size. And if it does not return, that means it becomes a plastic what? Material. And if the plastic material still undergoes stress as a result of maximum load, the material may collapse or rupture or break. So let's see a problem from JAMB. JAMB 2014, question 16. It says a force of 500 Newton is applied to a steel wire. So we have a steel wire. The steel wire. We have a steel wire, which is the material. Steel wire, which is the material. So it has a force of 500 Newton is applied to a steel wire of cross-sectional area. So the area is 0.2 meters square. Now, the tensile stress. So let's assume this is the wire. Okay? From here to here is the length of the wire. Now, but this material undergoes stretch. So because it undergoes stretch, there will be elongation. To elongate. So there is a new what? Extension. Okay? Because of the new extension, we now have L plus what? Plus E. So there's an extension as a result of stress. We have what? This material undergoes stress. And such stress is a tension, it's a tensile stress. Tensile stress, you are stretching. While compressive stress, that means you are compressing, you are squeezing the mechanical material. Now, the question says, what is the tensile stress applied to this material that enable these elongations? So what we have is that stress, sigma is stress. So stress is force applied on the surface of that material over area. So what's the force? 500 over, is the unit correct? Area is 0.2. So what do we have? If we do that, that's about 2. This will give us 250. Okay, so that's about 2.5 times 10 raised to power 3 Newton meter per meter square. So that is the stress, tensile stress. Okay? That is that on JAMB 2014. So let's see more questions. So So the correct answer there is B. We have another question. 2014 JAMB. Okay, 2024 question 29. 29. A spring with a spring constant. So we have a spring. This is a spring with a force constant of 50 Newton per meter. Is compressed from its natural position by 1 centimeter. So here, this one is called the equilibrium length. But we're told that it was compressed. So because it was compressed, you now have something of this form. It was compressed. So we have, let's say this is L. We can call here the extension. It was compressed. This is the original length. Okay, let me just use maybe L2, L1. Now, so it was compressed from its natural position by 1 centimeter. So by 1 centimeter. Maybe initially from here to here is 2. It was compressed by 1 centimeter. Calculate the work done by the spring on the object compressing the spring. So work, what is work? 1/2 Fe. We don't have force, but we have force constant. So there is a relationship. F equals to Ke. So K is also F over E. So where we have F, we place Ke. So the work done, 1/2 Ke square. But mind you, the extension is 1 centimeter. So over 100, 0.01 centimeter. Okay. So now, the work done is 1/2 times K. K is 50 times the extension. The extension is 0.01. So we can have 25 times 1/100. Okay. And that is just 2.5 times 10 raised to the power minus 3 joules. Because this is 2.5 times this is 10 raised to the power minus 2. I'm sorry, this is 25. So if I need a decimal point, if I move, I'll have, so 2.5 10 raised to the power minus 3 joules. So the correct answer there is B, 2.5 times 10 raised to the power minus 3 joules. So that's on JAMB 2024, question 29. So let's see another problem. 2021, question 32. So question 22. So we have JAMB 2021, question 32. Determine the energy stored in an elastic material whose force constant, so the force constant, K is 1.2 times 10 raised to the power 5 Newton meter inverse. And the extension is 2.0 centimeters. So determine the energy stored. So we know that energy stored in form of work done rather is 1/2 Fe. And F is Ke. So W is equals to 1/2 1 over 2 KE squared. So 1 over 2 times, this is going to give us 0.02 if you divide by 1,000 by 100. So 0.02 times the first constant, 1.2 times 10 raised to power 5. So if we do that, we have 1.2. So let's use our calc and see. So 0.02 times 1.2. So divide by 2. Okay. So that is square this. So if we square that, we have 24 joules. 24 joules. Let's see again. 0.02. Okay. Times 1, 2, 3, 4, 5. 40. Times 1.2. 48. So you have 48. 48 over 2 is still 24. 24 joules. So the correct answer there is E. The correct answer there is A. A is 24, so 24 joules. Okay. We also have question from 2008, question 15. JAMB 2008, question 15. A spring of force constant, 500 Newton. So force constant K, 500 Newton per meter, is compressed such that its length is shortened by 5 centimeters. So a spring, let's say we have a spring here. This is a spring. When it was compressed, we have something in this form. Okay, let's say from here to here, our length is 10 centimeters. So when here is now compressed to 5 centimeters. Okay, so it was compressed. Now, it said the energy stored in the spring, okay, shortened by 5 centimeters. So extension, we have 5 centimeters. So that's 0.05 meters. Energy stored again. The energy stored is equals to 1 over 2 KE squared. 1 over 2 times 500 times 0.05. Okay? So we can have 250 times 0.05. That should give us, let's see. So 250, there is a square. So sorry, a square here. Square. So 250 times 0.05 and 0.05. So it's 0.6. Okay. So it's about 0.625 joules. About 0.625 joules. So the correct answer, let's check the options. 0.625. So that's A. Correct answer is A. Okay. So let's say another problem. JAMB 2007, question 30. Question 30. So we have JAMB 2007, Question 30. It said a string of length 4 meters. So the length is 4 meters. Is extended. So there's an extension extended by 0.02 meter. So let's assume this is a string. Let's assume this is a string. This is 4 meters, right? But it was extended. It was what? This is the initial length. There was an extension. So it was extended by 0.02 meter. Maybe as a result of tensile stress, it was extended. Now they say when it was extended when a load, there was a load, we have a load of 0.4 kg is suspended on its end. Now, what will be the length of the string when the applied force is 15 Newton? So that means E1, there was an extension of 0.02 when F1 is equals to mg. Now, because the load is acting under gravity, we have mg as 0.4 times 10. That's about 4 Newton. So at 4 Newton, the extension was 0.02. The question now is, what is the extension and what is the new length when we now have a force of what? 15 Newton. So when a force of 15 Newton, so we can apply our change of state. E2, we don't know. Obeying Hooke's law, F is directly to K. Sorry, F is directly to E. So F equals to KE. So K is F over E. So F1, E1. F2, E2. So that means F1, E1, F2, E2. Now, what is F1? F1 is 4 Newton when the extension is 0.02. Equals to, what is F2? F2 is 15, but the extension, we don't know. So E2 is 0.02 times 15 over 4. So E2 is our calc. So 0.02 times 15 divided by 4. So we have about 0.075 meters. So the question says, what will be the length of the string when the applied force is now 15 Newton? So the length, L2 now, is what? What do we have? 4 meters plus 0.075 meters. Because the actual length was 4 meters, right? But when there was a load of 4 Newton, there was an extension of 0.02 meters. So when there is now a load of 15 Newton, there's an extension of what? 0.075. Because the force is directly proportional to the extension. The more the force, the more the elongation. So if you check at 4 Newton, it was 0.02 meters. But at 15 Newton, it was 0.075 meter. That means Hooke's law has been obeyed. The more they apply force, the larger the extension that will be produced. So L2 is 4.075 meters. Okay? And that's approximately 4.08 meters. So the correct answer there is D. Correct answer is D. Thank you, viewers. That will be all for now. Thank you.